let's continue with our examples of groups. The next example is something, again, we have studied quite a lot in our course, namely the roots of unity. And let's first look at a particular case, namely the fifth roots of unity. So sort of 7a here, the fifth roots of unity. So we have this picture, right? One, the real axis, the imaginary axis. We draw the unit circle. Okay, and we have these five fifth roots of unity. That form this really pretty picture of a regular pentagon. And we defined this as zeta 5 as cosine 2 pi over 5 plus I sine 2 pi over 5. This one was actually cosine 4 pi over 5 plus I sine 4 pi over 5. And that's the same thing as zeta 5 squared. Here is zeta 5 cubed, cosine 6 pi over 5 plus I sine 6 pi over 5. And finally this one was zeta 5 to the 4, which was cosine 8 pi over 5 plus I sine 8 pi over 5. And I claim that these fifth roots of unity form a group under multiplication. So first of all, I need to know that when I multiply two fifth roots of unity, I get a fifth root of unity. But you already know that, right? This is nothing new for you. And in fact, let's just make a general statement here. So if alpha and beta are nth roots of unity, then let's see what happens if I multiply them as complex numbers, right? This is multiplication as complex numbers. How do I check if something is an nth root of unity? I just raise it to the nth power and hope to get 1. So if I raise it to the nth power, I get alpha to the n, beta to the n. Oh, but alpha is an nth root of unity, so this is 1. As alpha is an nth root of unity. And so is this. As beta is an nth root of unity. So this whole thing is 1. So as a conclusion, I say that alpha beta is an nth root of unity. So if I multiply two fifth roots of unity in particular, I get a fifth root of unity. In other words, multiplication of complex numbers gives me a binary operation on the set of fifth roots of unity, or in general of nth roots of unity. Is the multiplication associative? Well, it's a multiplication of complex numbers, so it is associative. Is there an identity? Yes, 1 is the identity for multiplication of complex numbers. It's also the identity for multiplication of fifth or nth roots of unity. And it is a fifth root of unity. 1 is a fifth root of unity, 1 is a cube root of unity, 1 is an nth root of unity for any n. So 1 is the identity here. And does every fifth root of unity for now have an inverse? Yes, you can sort of read it from the picture. So the inverse of zeta 5 is zeta 5 to the 4th, because zeta 5 times zeta 5 to the 4th is zeta 5 to the 5th power, which is 1, because zeta 5 is a fifth root of unity. So its 5th power is equal to 1. What's the inverse of zeta 5? Sorry, shouldn't write it like this. Zeta 5 squared inverse Well, that's zeta 5 cubed. And then so on, right? Zeta 5 cubed inverse is zeta 5 squared, and zeta 5 to the fourth inverse is zeta 5. And of course, 1 inverse is 1. So every fifth root of unity has an inverse. But more generally, I can also prove that any nth root of unity has an inverse which is an nth root of unity. So let alpha be an nth root of unity. Consider 1 over alpha as a complex number. Okay? So you just say you're cheating here because you're already saying that alpha has an inverse. You're writing 1 over alpha. When I write this, I consider alpha as a non-zero complex number. And because complex numbers are a field, every non-zero element has an inverse. This inverse is a complex number. What I have to show is that it's actually an nth root of unity. Then, is it an nth root of unity? How do I check that? I always check such things by raising this element to the nth power and hoping to get 1. Oh, but this is just basic algebra, right? It's that. And alpha is an nth root of unity, so this is 1. So this whole thing is 1. So 1 over alpha is an nth root of unity. Okay, so what does this show? First of all, it shows that fifth roots of unity, but also in fact and completely generally nth roots of unity form a group. What's the binary operation? It's the multiplication of complex numbers. So maybe let's write this conclusion here. So the set of nth roots of unity with operation, let's erase that, being the multiplication of complex numbers is a group. And in fact, it has a special notation. It's this bold mu. It's mu sub n. It's an abelian group again. Abelian group. Why? Because multiplication of complex numbers is commutative. So it is an abelian group. So this example here is the group of fifth roots of unity. The identity, right, is always 1. So you see, the title of this lecture is Groups Are Everywhere. If you remember the beginnings of this course, when we first introduced the notion of a field, I could just at the beginning give you an example of 3 fields, and these were the rationals, the real numbers, and the complex numbers. And we worked quite hard to get more fields. So in some sense, the fields, at least when you start learning them, are like these rare animals, I don't know, like zebras or elephants that are rare and beautiful. Compared to this, groups are like ants. They just seem to be everywhere. Almost any structure that you study, there's also a group, and there are actually many more that do not come from rings and fields. So they are sort of ubiquitous. If you see one, there's probably more there, so you better call the exterminator if you see one. But they're also beautiful. So let's continue with more examples. So we now know that any ring gives examples of at least 2 groups. One is I take that ring and look at only the addition, or I take the units in that ring and only consider multiplication, and then there are roots of unity. Any nth roots of unity form a group. But there are more. So let, I don't know what the number were, I think number 8 maybe now. Let V be a vector space over a field F. Then this vector space, but only together with addition, so this is now only the set of vectors, is an abelian group. So when I write V and say it's a vector space, it already comes with two operations, addition and scalar multiplication. So now I'm saying, all right, I'm sort of abusing notation here, because then I'm writing this V here and I only mean the set of vectors. Strip it of all the operations, and then restore the operation of just addition of vectors to it. So any vector space under the operation that is just addition of vectors is also an abelian group. Why? Well, addition of vectors is a binary operation. It's associative by definition. There is the identity, namely the zero vector. So E would be the zero vector. And what's the inverse to any vector? That's just the negative of that vector. For any vector V in V. So again, a huge family of groups. Any vector space can be thought of as a group if you forget about the scalar multiplication. So in fact, this field here, I wrote this as a vector space of a field F. This field plays no role in this group structure. The scalars are completely unimportant. There are other interesting examples. 5. Consider, so let F be the set of all functions F from R to R. Now, this is an enormous set. It's not even countable. Any function, not just continuous functions, any function from R to R. Okay? And I just consider the set of all such. So, f of x equals x squared, f of x equals x cubed, f of x equal to 1 when x is rational and 0 when x is irrational, f of x equal to 0, so constant function, f of x equal to 7, another constant function. These are all examples of such functions. So now I'm going to define a binary operation on this set. So define a binary operation star on F by F star G. Okay, so this is supposed to be a function from R to R. So how do you define a function? Well, you just tell me what it does to a number, to a real number. So when I apply it to a number x, real number, I define it to be, this column means I'm defining it, as f of x plus g of x. Okay, so I'm just adding the values. All right, and I mean, really, nobody really denotes it by star. People denote it by plus here. Okay, but I just wanted to stress that that's how you add them. So adding functions is the same as adding their values, according to this definition. Okay, so if I do this, is this a function that takes real numbers to real numbers? Yes, sure, right? All real numbers are in the domain of f, all real numbers are in the domain of g. So I can evaluate both of them. Both of them give me a real number. I add them, and because real numbers are a group under addition, this gives me a real number. So this is a function from R to R. So this does define a binary operation on the set of all functions from R to R. What's the... is it associative? Yeah, because the addition in real numbers is associative. Okay, so I'm leaving it for you as an exercise. Check associativity. But you will see that it all boils down to associativity of addition of real numbers. Right, so you need to check that f star g star h is equal to f star g star h. So you evaluate both of these sides at x, and you have to show that they give you the same thing. What's the identity for this? It's the zero function. The zero function, i.e. it's a function, let's say e, such that e of x is equal to 0 for all x in the real numbers. Okay, well, I mean, just look. If I take any f and I star it with e of x, then by definition that's f of x plus e of x. Oh, but this is 0 by definition, so this is just f of x. Okay, so, and of course if I do it the other way around, I get the same thing. So this is the identity. What is the inverse? It's actually just the negative. So f inverse of x is the same as just negative of f of x. You have to be sure where this negative is taken, right? This is a real number. So this is just the negative inside the real numbers. In other words, the additive inverse of f of x inside the real numbers. So as x changes, right? X is a real number you plug in, you get different values. So in a sense, so for example, the inverse to the function f of x equals x squared is the function f of x equals negative x squared. So this is a group. So f with star is a group. Again, an abelian group, because addition in the real numbers is commutative. And now you see that actually this gives you a possibility of building a lot of such examples, because it doesn't have to be the real numbers here, it could be the complex numbers. Okay, this also doesn't have to be the real numbers. You can manipulate the domain and the range, the domain and the codomain quite a lot here. Continuing with this example, 6. Let C be the subset of f consisting of continuous functions. Is C, together with the same operation, a subgroup of f? Let's think about it. Does the addition of functions defined this way restrict to a binary operation on C? If I take two continuous functions and add them like this, do I get a continuous function? Yes, you know that from calculus, maybe, topology, analysis. The sum of continuous functions is continuous. Is this a continuous function? Is this 0 a continuous function? Yes, right? Constant functions are continuous. And finally, if I take the negative of a function, that's still a continuous function. Negative of a continuous function is a continuous function. So yes. As sums of continuous functions. Sums and negatives of continuous functions are continuous. And the 0 function is continuous. let's go on with that. 7. Let C infinity be the subset of C. Oh, let's just write off F, okay? Of consisting of functions of differentiable functions. So that means derivatives of all orders. Is that a subgroup? So, is C infinity with a star a subgroup of C with a star? And this I know is a subgroup of F star. All right, let's see. So this is differentiable functions. That means they possess derivatives of all orders. These are functions from from R to R. Differentiable functions are continuous. That's one of the theorems in analysis or calculus. So this definitely is a subset of that. If I add two differentiable functions, do I get a differentiable function? Yes, because that's how derivatives work. Derivative of a sum of a function is the sum of derivatives, which really boils down to the fact that limits of a sum of two functions is a sum of the limits. So the binary operation restricts to the set of differentiable functions. Negatives of differentiable functions? Yes. If a function has all the derivatives, its negative also has all the derivatives. And in fact, the derivatives are just equal to the negatives of the derivatives. And finally, is the zero function differentiable? Does the zero function have all derivatives of all orders? Sure. Yes, all of them are actually zero. So yes. And in fact, being a subgroup is transitive. So that means this is actually a subgroup of that. I'm not going to get into this. This is just sort of a trivial exercise to show that if H is a subgroup of G and G is a subgroup of K, then H is a subgroup of K. Okay. Let's stop here, and in the next video I'll show you even more examples.